A lot of you were at the Build conference and got to see some of the AI talks. And there's a lot of exciting things going on in AI in general, machine learning and image recognition. I've been kind of into computer vision for maybe a decade now or so. And if you are going to delve into the image recognition and things like that, some of these other aspects of computer vision will actually be very helpful as well if you don't just like playing around. So alternate title, The World in Computer Vision, because that's really what computer vision is about, is a computer seeing the world through either a camera or some other sensors and understanding some aspect of what it's seeing. And so another way to think of it as reverse graphics, right? Because graphics, you have a model of some virtual world and then you render it in 3D or in 2D. But in computer vision, you're taking a rendering, which might be an actual picture of something, and trying to build a model from that. Not necessarily a complete model, but a model of some aspect. So what I want to do is just kind of go through, give an overview of what all is out there in computer vision and what you can do with it. Have a couple, maybe one or two applications in there, and then we'll look into a real example and some code, some C# code for computer vision, a specific problem. So to start with, you have some sort of sensor. Usually you're talking about a camera, but not always. You might have a single camera monocular vision, or you might have stereo vision, which typically referring to two cameras looking the same direction, much like human eyes, and a known distance, and that can give you depth. You might have multiple cameras from different angles. Besides cameras, though, you can have a laser rangefinder, which will give you a map of what the depth is from a certain point, either at 3 degrees of freedom or in a certain frustum. And then there's what they call RGBD cameras, which besides color imagery, it also has a depth component, which can be accomplished in different ways. The famous example is the Kinect sensor, which uses infrared light to get that depth component there for you, which can help you reconstruct 3D scenes, do all that analysis. But really, computer vision could be dealing with any type of geometric representation of the world or some part of the world. So let's look at some of the low-level things. Low-level computer vision really is mostly the image processing. It's always going to be an important aspect of your pipeline that you go through to build your model. You're always going to need some of these components. Just to make sure we're on the same page as far as image representation, we're typically thinking of a two-dimensional array, X and Y, or often called a matrix. But at some point it's represented as a one-dimensional array because, of course, computers store their memory in a single address direction. That can be important in optimizations because every time you're doing a two-dimensional axis, you're multiplying and multiplying. So if you're doing optimizations, you don't always have to do it X and Y. You can just spin through all the pixels as a one-dimensional array. Important to keep in mind. You're dealing with one or more channels. So each pixel has, in a grayscale image, it has one channel, which is just the brightness of the pixel. But then in a color image, you're going to have 3 channels. One channel could be a binary image, black and white, which is often used for segmentation to say, I care about these regions of the image and not anything else. In grayscale, it could be 8-bit unsigned, so 0 to 255, or a lot of times it's also important to use floating points sometimes. So each pixel will be represented by a floating point number, which is important to not lose precision in certain calculations. So it can be represented in these ways. Color, of course, can be 3 channels, but you have different spaces. You always hear about RGB. Oftentimes it's actually in the order of blue, green, and then red. But then there's also other color spaces like HSV is a very common and useful one. Hue, saturation, and value. So you think of the color wheel when you're using a paint program or something like that. You're dealing with how much color is the saturation, and the brightness is the value, and the hue, of course, is your color spectrum. Sometimes you have an alpha component if you care about how to mix things. We talked about the importance of floating point. So a lot of times when you look at computer vision algorithms, you're going to be seeing grayscale images, not color. And the reason for that is if you're going to be processing 3 channels instead of 1, obviously you're going to be doing about 3 times as much computation. And so you use color judiciously. You only use it when it makes sense, when you need to. If you're trying to sort out different vegetables or fruits, color is actually a very important component to differentiate blueberries from something else around. But otherwise, a lot of times you'll use grayscale. So, some basic image processing, some things we can do with our images. Just to spin through these. Some of these will probably be very straightforward. You already know them probably. So you look at something like inversion. So for all the pixels in the image, the destination pixel at XY will be, assuming we have like 8-bit unsigned values, 255 minus the source XY. So a bright pixel becomes a dark pixel and vice versa. I'll go ahead and represent this as, in a more compact form, each destination pixel equals 255 minus each source pixel, the corresponding pixel. That's actually how you see it usually when you're using a computer vision API. Is you're not going through 4 loops. You're just doing a one-shot. Add this image to this image, and what you're saying is take each corresponding pixel X and Y and add them together to produce my destination image. So that's a good way to kind of think of it. Brightening an image, you're just adding a fixed value maybe to each pixel, and of course you have to think about capping that value to the maximum value, so that's why you might represent it with a min function to make sure you're taking the less of 255 and the brightness value. Changing contrast, you can simply multiply and then add by some offset. And then shifting or scrolling the image is simply assigning each source pixel to a destination pixel offset by some X and Y. So these are basic pixel by pixel operations. Multiplying one image by another will basically mask the image. So any full value, like if you're thinking of the mask as 0 to 1, then any pixel value multiplied by 1 is going to be that pixel. And then so if you can even do, if it's floating point, you can do a kind of a fade out. You can have kind of 0.5s in there and 0.6s and so forth. And when you multiply, that's what you get, is basically a masking operation. Subtraction is important. When you're subtracting one pixel value, when you're subtracting 2 images, you're getting the difference between the 2 images. So that can be important for image segmentation. So if you know, for example, we'll look at an example a little later, but if you know, like if you have a fixed camera and it's looking at some scene and there's no objects in it, if you take that picture and then you have something, a person walking into the scene, you take that picture and you subtract that from the background, you're going to end up with all black except for the person. And so that can separate out, the new object from the old. So subtraction can be pretty important there. And then thresholding is an important operation as well, because basically a lot of times at some point you're deciding, do I care about this pixel or not? It's a yes or no, so you need a binary representation. So that looks like if the source pixel is greater than some threshold value, assign a 1, otherwise a 0. So we're converting, in that case, a grayscale to a binary image. As I said, important for segmentation, to threshold to say, so like with that person, when we talked about subtraction, you might threshold the image with just the person in there to say, yes, I care about these pixels where the person is and not about anything else. But the challenge in thresholding is to find the right value. Because if you look in this chessboard image, if we were trying to get the checker pattern, we didn't do a very good job because these squares over here are all black and some of these are all black. And so we didn't get the right threshold value if that's what we were trying to do. So you can determine it manually, say, oh, that was too dark, I need to bump it up a little bit. But that only works if you know exactly where your input's going to be. Most of the time, you're getting new images, so you have to find a value that'll work with any image in your application. So then you could get the average of all the pixel values, the mean, and use that average as a threshold. Sometimes that can work. Sometimes a better choice is the median, because that'll kind of take into account the middle value instead of just the average. There's something called entropy minimization, which is basically, like if you look at the chessboard image, entropy minimization would be trying to get rid of a bunch of clutter, basically. Let's put it in simple terms. Global value method is kind of important, or interesting. Basically, if you take a histogram of the values and say you have something like this, then the global value method is just finding, okay, where's the real separation? And so in this case, it's pretty obvious. This valley here, the global value, this is the lowest point. This is the biggest dip in everything. So this is probably where it makes sense to separate the image, and that can be pretty successful. It also supports multiple thresholds. So sometimes you don't just want yes or no. You want maybe 3 different levels or 4 different levels. So you can find the two biggest values, or the 3. So 2 biggest values. You have 2 thresholds, and 2 thresholds, and then you can divide it into an image of 3 different values for each segment there. That's an advantage there. But sometimes when you're trying to separate out parts of the image that you care about, sometimes thresholding isn't really going to cut it. You're going to have to use something like edge detection, which we'll look at. But adaptive thresholding is really useful, especially when you have inconsistent lighting. So look at this example. Say we have this page, which in the real world is just black text on a white page, and what we want is the text, because we're doing OCR, which is optical character recognition. We're trying to get the word, what are the words on the page, and convert that to an actual string we can use. But if we use a straight threshold value, this is what we get. Because if you see the lighting problem here, it starts really light, maybe because of the bend of the page, or just the diffuse of the material. It starts out light and gets really dark. So if you choose any fixed value for the whole image, you're going to get a bunch of dark area and then a bunch of light area. So adaptive threshold basically takes which one's the dead one? I laid them both down together. This is the dead one. Adaptive threshold. Here's your image. It slides a window across for each pixel in the image. Slides a window, and a lot of times it'll use a mean or a median. And it'll say, what's the average intensity value, brightness in this window? And then, so if you're using mean threshold, it'll find the median and use that as the threshold for that pixel. And then it'll slide that window a little further to the next pixel and decide the threshold for that pixel. And so you get a different threshold for all the pixels. And when you do that, and you average for the light area, you're going to have a higher threshold. For the dark area, you're going to have lower threshold in those pixels. And then you end up with a nice solid text there. So that's adaptive thresholding. So if you decide to try stuff out, that's a good one to keep in mind. Okay, so with thresholding, then you end up with the binary image. Then there's a number of things we can do with that binary image. Hopefully this isn't getting too boring yet, because we're going to jump into some interesting stuff. Or if it's not interesting yet, we'll look at an actual application. But so once you have your binary image, you can do what's called erosion, which, let me see if I have an example. Yeah. So erosion takes each shape, if you will. In this case, we're eroding the black pixels. And it takes each shape and it makes it smaller. It eats into the edges, it erodes the edges. So basically the equation is, assuming we have all the pixels are 1 and 0, right? Then if the sum of, if we're looking at a 3 by 3 window, if the sum of the 8 surrounding pixels is 8, in other words, if they're all on, then we assign a 1. Then only then does the pixel in question get a 1. But if any of them are off, we assign it a 0. I don't know if that makes sense. But each pixel in question, we're saying, should this be on or off in the erosion? So if some of these, but not all of these, are on, then we're going to turn this off. Because there's not enough shape there, we're going to erode. We're going to make some black pixels go away. But the important ones we're going to keep. The important ones being when it's surrounded by on pixels. So that can get rid of, as you can see, this pepper noise here, salt and pepper noise. It gets rid of a lot of that. That can be useful for that. But another interesting use is separating items if you want to count items. So for example, this picture of some coins here. And they're touching, so if you're trying to, if you picture trying to count these out, like if you took this into a paint program and you did a flood fill, it's gonna fill out, when you click one coin, it's gonna fill out other ones. And so basically when you're counting objects in a binary image, you're doing a flood fill and filling one, and then you look for the next one, fill the other, okay, I have 2, and so forth. So the problem here is when we threshold that image, we have all these connections and we can't count them. So with erosion, then this is what happens, and now they're nice and separated and we can count them. So just that simple erosion operation can be useful for that. And then the opposite of erosion is dilation, making things bigger. So if we have any surrounding pixels that are not off, then we assign a 1. Otherwise, we're going to assign a 0. And so interestingly enough, if we have kind of groups of individual items, we can group those together using dilation, and then the computer, the algorithm can figure out we have 3 groups by labeling connected regions.
Is these two processes, is there any other use for them other than just counting?
Erosion and dilation?
Yeah.
Oh, yeah, there is. For example, sometimes, well, we're going to look at this. Oh, here we go. I'll explain it right here. No, it's a great question. And that's a great question. I'll go ahead and explain this, and then I can explain that question. And actually, I welcome any questions. It's fun to discuss this stuff, and I don't want to leave anyone wondering about anything. So let's look at the problem of motion tracking, right? So we talked a little bit about it. You have a camera. In this case, we'll make it a fixed camera, no panning or tilting of the camera. So we can have a simpler algorithm that way for this example. And so what we might have is, as we talked about, in the simple case, ideal case, you have an opportunity to capture the background without any objects in it. So you know what that background looks like. So first step, we capture the background. Then, as we mentioned before, subtract the current frame. So as we process a video, we're talking about, say, real-time video here. Our algorithm is going to take each frame of the video. If you have 15 frames a second, you can take each of those frames and put it through our pipeline. And so we're talking about one frame here. Once we've captured our background, we subtract the current frame. So here's an example where I've captured the background and there's 2 people walking around on grass, and we subtracted the image. You can actually, in the difference, because of the shadow, you can see the grass, which is kind of interesting. Excuse me. And so then the next step is to threshold those. So then we're basically saying, these are the pixels that we care about. And see these speckles here, we could use erosion to get rid of those. But Now, for Marx's question here, this is where it's important. You see, this person, his foot is detached from his leg, ouch, and the same here. This person, their legs detached, and so, well, so we can use dilation to connect those, which is kind of the same use of the counting problem, or the grouping problem, except that in this case we're just trying to determine what blobs of white pixels are one object, based on proximity. Other uses, we'll get to a couple other uses too for erosion and dilation. So, yeah, so because of that problem of separation, then we dilate. In this case, this is something I did about 8 years ago in Java. It's actually available open source. But in this case, I just did pixelation. It was a lot faster than the actual erosion algorithm. So pixelation is just sampling every, say, 3 pixels and saying, is it on or off? I might have done a max, like if any of them are 1, then yeah, I think I did that. If any of them are on in that square, turn it on. That just dilates everything. So now we have nice connected people. They're not in pain or anything. And then the next step is to label the blobs, because if you think about it, if you're writing the code and you're trying to say how many people are in this scene, then and so you look at each pixel, you don't know which object that pixel belongs to. So you have to have a way of saying, excuse me, this pixel belongs to object number 1, and so you're going to label all of these pixels a 1. And then you're going to label all these pixels a 2, so you can go back through the image and know which object it belongs to. So that's, here we've assigned a color to each label number. In this case, there's some inexactness. The shadow ended up getting detached here. So that's the thing with computer vision algorithms, is it's hard to make them robust, and they use that term a lot because that's the biggest challenge. It's not just can you get it to work sometimes, but can you get it to work all the time in your situation? But anyway, the next step in motion tracking is we're not just interested in detecting that there's motion there, but we're interested in tracking where that object is going. So, in other words, if we label this 1 and this 2, next frame we don't want to start labeling this 1 and this 2. We want to correlate the objects with each other across frames. So, once you have your blob, you can create this bounding box, just basically finding the min xy and the max xy of all 1 pixels. That'll give you your bounding box. And then with that, you can just take the centroid, the center of the box. And probably the easiest way, it depends on your application if it's sufficient enough. The easiest way to do correlation then is just proximity. Say, okay, the next frame it moved this much, and this object moved this much. Like, so this blob, which is it closer to? Is it closer to in the previous frame, right? So the previous frame there was this rectangle and there was this rectangle. Well, it's obviously closer to this rectangle, so it's probably the same object. So that's one way of doing correlation. And I think that's how I did it here. There's challenges. You always got to look at your corner cases. So for example, if you have 2 people and they walk by each other and they occlude each other, okay, now at this point they're close to each other. Boxes are going to be right by each other, so they might swap labels. So you have to. Then you might look at velocity, right? Okay, this one's continuing to move this way. They probably didn't do this, so you can use things like that. Yeah, then they definitely do that, right? So here's kind of the whole pipeline of actual implementation I did back then. And notice all this was basically just using those low-level operations we looked at, labeling. And if you're using a framework, I'll jump ahead a little bit. My go-to is OpenCV, and actually that's what most of the community is using, unless you're maybe working at a huge company that develops all their own algorithms, doing their own chips and stuff like that. But OpenCV, things like labeling blobs is a one-liner call basically to a function. So That stuff's really easy. So here's kind of the pipeline. One important thing that you're going to run into if you try this stuff out is, especially in an outdoor scene, the lighting's going to change. The cloud occludes the sun for a little bit, and then so things are going to be bright and then dimmer and then bright. So what's going to happen with our background image that we captured, and then you take a certain frame when it's darker and we subtract that, you're going to get a whole image full of pixels that we care about, right? And so those lighting changes. So you need a way to update your background model as lighting changes and things like that. That can be as simple as each frame, take the pixels that you know you don't care about, where you know there aren't any objects, which you might use what would that be, a higher, a lower, whatever it was, a different threshold to say, I know these aren't objects, and update those pixels in your background. And the way you could update it is just subtracting the current frame's background from the previous background, and maybe factoring that down so you don't just change your background model completely to the new frame, but you start to move that way. So you might make that change smaller and then add it to your background, if that makes sense. But so this is probably one of the simplest motion tracking algorithms you can do. Okay, so continue on with some more binary image operations. So opening and closing is just dilating and then followed by erosion. So closing, let's look at one at a time, right? So closing, the reason it's called closing is because when you have things that are close together, it'll close that gap. But notice when we dilate, it made those coins larger, right? But in this case, notice the J isn't really larger, because what we've done is first we dilated, so those connect, and then we erode, which gets that fat J back to a skinny J, but leaves that connection. Does that make sense? So, and then opening is similar. And these can be used to remove salt and pepper noise without affecting other objects. And in fact, if you do dilation then erosion, and then you do it again, dilation, erosion, anytime you repeat that, it's not going to make any difference after that point. There's a term for that, but I don't remember what it is. but so that's kind of good to know. It's not going to destroy your image.
So is that how, in that black and white image of the chessboard, is that how you would remove that shadow to make it a clear square before you actually started to, let's say, count pieces?
Yeah. Yeah, exactly. That'd be a good way, without affecting everything else, to remove a lot of that pepper noise from that shadow.
Okay.
Yep. Closing or opening, depending on if you have white on black or black on white. Yep, so convolution. This is a really important operation. A lot of operations use this. Well, let's go into detail. And this will also be important in machine learning, and some of the big things that are going on in the past just few years in machine learning and stuff that Microsoft and IBM and them are doing in their cloud services. So the general definition is the integral of function g over f. Who cares, right? But what it really comes down to, quite simply, is for each pixel, well, okay, yeah, for each pixel, going back to our window, right, our sliding window that we keep moving to the next pixel in the next row. For each pixel, we're going to take this some function, and it's actually, you might say xy, that says if, this is actually more like an offset. If you're at the center, you're doing the function at 0, 0, and you're saying this function determines the weight of each pixel in this window, and then adds those multiplications together. So you multiply each pixel by the weight given by whatever your function is, and then add them all together to get your final pixel. So mathematically, it's just a bunch of multiplications and then a sum. But what that does is what's really important. That g function is often called a point spread function, because you're spreading out pixel information to other pixels in the resulting image. So, so here's some operations you do. Oh, so something about that though. This function, it can be any function, right? But a lot of times that function is simply a mask of, in this case, where's the eraser? There it is. Nope. Yep. So like a mask of maybe of numbers. So you could have different numbers in here for your mask, and then in that case you're just simply going through with each sliding window and multiplying the values by the pixels and adding them together. So, and that's a specific mask right there. So some of the things you can do just with, in this case, just with a mask without actually a function, is you can do dilation erosion, both on binary and grayscale. You can shift the image. You can do edge detection. So here's an original image right here of this weird looking animal. What is that? Anyway, but I probably could, yeah. That's a good idea. So edge detection, so this was just, I think, a 3x3 mask right here. And it basically, it did a pretty good job finding the edges of its hairs and ears and things like that. And then noise filtering. Here's a, this is sharpening, sorry. I don't know if we have a noise filtering. So this is a Gaussian blur right here. That can be done with the convolution as well. And this is actually a I say Gaussian because that's how I used to always read it. I guess it's Gaussian, sorry. But anyway, this is a Gaussian approximation. So you remember the Gaussian curve, something like that. And so by blurring that way, and actually they'll take the sum, and then they'll divide it by the sum of these numbers to get it back normalized to the regular range of pixel values, if that makes sense. So that's a Gaussian. Sharpening you can also do with convolution. That has, you can look it up if you want. It has like a positive number here and some negatives out here. It's kind of interesting. Kind of basically you're finding the gradients, the change in intensity between pixels. So let's look at image filtering, because a lot of times you'll end up with noisy images and you don't want the noise in there, so you want to get rid of it. So one way of getting rid of it is the Gaussian blur. Excuse me. And so you can use these approximation masks. You can use a 5x5 or as big as you want masks, depending on how blurry you want it. And there's a very basic estimation, approximate Gaussian curve. Then you have that 1/16 one. But it's not very applicable, actually. I mean, yeah, it removes noise, but the other problem is, so Gaussian noise is kind of like consistent noise throughout the image that you get like from a CMOS camera in dark setting. But then impulse noise is where you have kind of like salt and pepper noise, where you have speckles. And the problem with using a Gaussian blur is it'll kind of take those speckles and it'll spread that value to other pixels and kind of smears that noise around. So it really loses information. You lose your edges and details, and so it's not usually good for computer vision. But if you're trying to get rid of noise, median filter it's pretty impressive what you can do with just simple little operations. In this case, you have a very noisy image, and then with a 1 pixel median filter, you get rid of a lot of the noise. There's significant. You can also, if you do a big enough median filter, or sometimes if you iterate, you can start to segment out the image. Like if you're segmenting by color, you can start to do that with some of these noise filters. Let's see how we're doing on time. Wow, it's going fast. Okay, then I'll go a little faster. If you're doing some image filtering, you look at your different options, and compare based on your your needs. So truncated median filter is more like a mode filter because it takes a histogram of the intensities and then uses that. Did the lights get bored? So yeah. So here's Gaussian blur compared to a median filter, iterated multiple times, and then here's a truncated median filter, a mode filter, iterated multiple times. You can see how it kind of starts to segment things out. Okay, so let me see how many. Okay, I have some slides to get through. Edge detection. So sometimes you're interested in the edges of things. So you take an image and you end up with an image where the intensity represents how confident you are that it's an edge. Of course, you can threshold that and end up with yes, it's an edge, no, it's an edge. It's not an edge, no, it's an edge. There you go. Some of the edge detection algorithms produce orientation. So not only does each pixel tell you if it's an edge or not, but it tells you which direction the edge is, which can be useful in some cases. Even a basic 3x3 mask can be used. You can use template matching. That's not usually very useful, so I won't go into that. Differential gradient, yeah, you're usually doing something like that. You're basically looking at the change of intensity from both in the x direction and the y direction. Now, if you have those two vectors, you can add them together to get the direction, right? Direction and magnitude, and then you normalize it to get the direction. Does that make sense? So like if you have a, yeah, that probably makes sense. Don't have to go into detail there. But it seems like kind of the go-to edge detection for most of the time is the Canny edge detection. So if you're using something like OpenCV and you want to find edges, you can jump to use the Canny function. And it'll produce something like this. Now, it's not always perfect. You notice this round part has a break in it, and then it continues and it has a break in it, so that's not always good. So in comes hysteresis thresholding. So basically all we're doing with hysteresis thresholding is first we find edges with something like Canny. Well, Canny actually uses hysteresis thresholding. So we find edges with something like the gradients, and then threshold that at a high threshold to say, yes, this is definitely an edge, and leave out the other stuff. And then basically use those little pieces of edges as a seed to find the rest of those edges. And the way we do that is actually pretty simple, just by then applying a lower threshold and making sure those pixels are connected to one of those high threshold points. And so then here's a neat little example of finding the lane markers. It has nice solid edges around each of those dashes. Okay, feature detection is important because say you're solving a problem on the assembly line, you're having a bunch of hardware going by. A lot of times you'll want to find corners. And so that's a feature. You find corners, and you know, if you're dealing with square parts, you can find its orientation and you know, do whatever you need to do. So just for finding corners and also finds other things like crosshair type things, you can use the Harris detector. But you can't use it to correlate, to say, okay, here's this feature in this image, and here's the same feature in another image. It's not going to do that for you. If you want to do that, you want to use something better. So SIFT is one example, the scale invariant feature transforms. So scale invariant meaning, okay, well, first of all, because these feature detectors have something called a descriptor. So when it finds a feature like a corner, it'll store kind of a little description, whether it's just a little grid of the gradients or changes in intensity. It'll store that so that next time you find features, say in the next frame of a video, you can look and see which of those correlate. So in this example, these lines are being drawn from the same feature and found in both images. So it's kind of hard to see the correlation, but if you look at this bottom line in this little spot here on that pedestal, and you follow it across, and it's that same spot. And so they use SIFT to find that same spot. So this is really useful in things like 3D reconstruction. Maybe you've seen where you can take multiple pictures from different angles and then reconstruct a 3D model of that, whatever you took a picture of. So this is part of a very important process. Part of the process is finding the correlating features, and then you do what's called a homography to find what's the 3D transformation between all those points. So that's really cool. But then SURF is typically a little better than SIFT. Is speeded up, is that really the right word? I thought it was sped up, but anyway. They always say speeded up. Maybe I have it wrong.
It's like wind and wine.
Yeah, right. What's the difference? So this SURF can track features even under rotation and 3D transformation. SIFT does somewhat, but SURF has a wider baseline, so you can go around the object further before the descriptor for that feature is too different to recognize it. So SURF's a little better at that. There's other methods you can always look into when you're trying to solve something. You kind of compare them. And then now we're starting to drift a little more into the machine learning side of things. The histogram of gradients, or HOG, was designed to detect people. Histogram of gradients, I don't need to go into the details, but basically, so it does take some training. You have to get some training data and train it, and then you have a HOG descriptor, and you can match them. But of course, if you're just detecting people, there's plenty of data sets already out there for detecting people. So once again, it's almost like a 1 or 2 liner in something like OpenCV. Texture analysis, we won't really go into because it doesn't seem to be used much anymore. It doesn't seem to be too useful to last. Well, anyway. But basically, texture analysis can do things like determine if the texture is grass or sand or trees, and so that if that's useful, you can look into that. But then now they're just using convolution neural nets for that type of thing, image recognition, which we'll look into. Okay. When should I stop, Brian?
Never.
When I'm done? Never? Because, okay, I don't want to go too long. Let me just kind of run through these, and then we'll get into some actual code. So intermediate CV, I'll just kind of tell you what's out there, and you can go look at something if you're more interested. Blob labeling, we've already looked at, labeling the different blobs, 1, 2, and so forth. Boundary analysis, you can analyze so when you find your edges with something like Canny, then there's different things you can do with analyzing the edges. You can use it for classification, where you say if it has this changing radius of this shape, and find something else like that. You can use it kind of for correlation or that type of thing. There's lots of different methods there. Skeleton tracking. So if you think of something like the Kinect, and it's following your movements with your limbs, and it's doing skeleton tracking. So it'll take the blob, that's you, and it'll thin you to a stick figure basically, and then find the contours and then do some skeleton analysis. Shape detection, if you need to find lines, if you need to find circles or ellipses. So once you have your threshold image or your edges, you can run something like the Hoff transform, Hoff, I don't know. The Hoff transform to find lines or circles. That's another one-liner in OpenCV. So if you're trying to find coins or whatever. You can do some interesting things with that too. Like if you have lines, like say road lines, and you want to figure out at what 3D angle you're looking at it, you can look at convergence. Where do those lines meet? And then that's your kind of, if you remember art class, doing your convergent points to do your 3D. You can kind of figure that out. Object segmentation, we've kind of talked, that's basically just separating out, what you care about, what you don't care about. And optical flow is really interesting. You can take two images or a sequence of images, frames, and for each pixel you can say how much has this pixel moved since the last frame. And so if you're walking forwards and you take two frames, you do that, you get this kind of Star Trek shooting stars effect, because the pixels out here, they're closer to you, so they're moving more, kind of the spread type of thing. And the ones further away are moving a little bit. And you can use that for 3D analysis as well as just two-dimensional analysis. A couple things about three-dimensional computer vision. So you can determine the shapes of objects from shading. Like if you have consistent color on an object, there's algorithms for finding like a sphere. It's going to, with the right lighting, you're going to find shading. You can find its shape, or from texture if you have a consistent texture that's bent around something. Shape from silhouettes is interesting. If you think about the motion tracking, and if we did that in two cameras, so then you have this white blob person here from this view and the same white blob person in the other view, then we're calling those silhouettes, okay? So then if you know the relative angles of those cameras, you can basically shoot rays, if you will, and see where they, for each of those blob pixels, you shoot rays and see where they intersect, and you end up with a volume for that person. And so now you have like a shape. And more views you have, the better shape you can get. Stereo correspondence is just the problem of when you have two cameras, figuring out the depth at each point in the image, how far away is each little point in the image. There's lots of algorithms for that, lots of work there. Multi-view reconstruction we kind of already talked about with the feature detection, taking pictures of the same thing from different angles and then reconstructing. There's several different major methodologies there. Visual odometry is the process of trying to figure out how you've moved based on a sequence of images. So like we talked about optical flow, that's visual odometry if you're trying to use that to figure out where you've moved through a scene. SLAM is related, simultaneous localization and mapping. So if you think of what you do when you walk into a new building, you're thinking about where you are in the building and you're also kind of mapping out what's in there. Won't go into details. I do want to show one video of a really good algorithm for SLAM. This gets me excited. So they have a camera moving through, I think it's like a subway. Oh, you can see it up there. It's like a factory or something. And you can see all those dots. That's the feature tracking. And then the color is representing the depth. And so just from the sequence of images, they're finding all these points and modeling them in a 3D map of the whole environment. So you're mapping and you're localizing. You know where you are and what's around you. So it's very cool.
Just a plain old camera?
Yeah, RGB. Yeah, just a camera. And so there's a lot of progress being made there as well. Of course, HoloLens uses a lot of that technology, SLAM technology. Okay. Machine learning. So convolutional neural networks. You've probably heard of artificial neural networks, kind of inspired by the brain, and it's been around since at least back in the 80s or 70s. But if you think about trying to recognize an image, is this a dog or is this a cat? And if you take a neural network, it's basically all these inputs, and then you have an output for each thing you want to classify. So dog or cat, and then whichever one comes out the highest, that means we're pretty sure it's a dog and not or a cat. Your inputs can be anything that you're determining. So if you're classifying an image, you would think to take every pixel value and map that to an input. But the problem with that is for each input, then you have these middle layers that all connect to each other. So you got this like big O, I don't know, what is it, at least n squared there. But then, so if you're looking at an image x by y, you're looking at n squared times n squared, and to the fourth, you're gonna do a ton of computation, so it's just not practical. So convolutional neural networks basically kind of solve that problem. We talked about convolution, And basically the idea is just to take recognizing that neighboring pixels are going to have something to do with each other. They're going to be related more so than pixels over here. So just in short, it's taking advantage of that knowledge to reduce the number of connections, the number of computations. It's not really 4 years old technically, but some major leaps have been made in just the past few years. And a lot of state-of-the-arts, and what I mean is like different problems you're trying to solve in computer vision, a lot of those are now, the state-of-the-art is like the best current algorithm, the most robust algorithm and so forth. A lot of those are becoming CNN-based just because of how good this is. And what it basically does, like if you think about that motion tracking problem we looked at, CNN will kind of learn what filters to use. So, you know, to use thresholding and then dilation and so forth. So, because what you do with a neural network is you train it by saying, here's an example input and what the output should be. You use what's called backpropagation to adjust the values to say, well, that wasn't the right answer. Let's adjust things a little bit. And you continue that training. And so you train this, and it forms kind of these equations, if you will. So that's the exciting thing is instead of, a lot of times you'd spend, you know, as a computer vision scientist, you'd spend, you know, weeks or months trying to solve one problem. But if you have enough training data, you can just throw it at a CNN and it'll solve the same problem, and a lot of times even better than the way you could solve it with traditional computer vision. The challenge though is having enough training data, because you need a lot of training data. But sometimes you don't need a CNN, but so that's where you're seeing a lot of cloud services now popping up that use CNNs for image recognition. And Microsoft, I think, has a variation on CNN, but it's related.
Is it Microsoft's
Cognitive.
Azure Cognitive Services?
Yep, that one, yeah, and then
Video and facial recognition.
right, all that recognition, and I think if I remember right, like pretty much all of it's recognition problems, and so it's all very related. But so there's a lot of cloud services out there because they want your money, right? And they're solving a really good problem. But you can still do it on your own box. You know, you don't have to use a cloud service. And there's pretty good APIs. Just real quick, I want to throw at you some development tools that are available for doing computer vision stuff. OpenCV, I've mentioned already, has huge community, thousands of algorithms. It's mostly C++. There's a couple C# wrappers, one called MGU CV. It's kind of expensive, $400 for a single developer, but it's one-time cost. Might be worth it. I used OpenCV Sharp 3, which is a open source wrapper around OpenCV, C# wrapper. BoofCV is a Java one we probably don't care about here. And then Halide. Okay, so if you're doing low-level computer vision, you're doing your own algorithms, this is more low-level. This is a really awesome way of separating algorithms from optimizations for specific hardware. You can do different optimizations but keep your algorithm code the same. So Halide is really, really neat for that. And then there's a lot of specific libraries, including open source ones for specific problems like reconstruction and SLAM and so forth. I tried LiveBlocks, which is like a drag and drop type thing. I couldn't figure it out, so it wasn't turned out to be useful. Hardware accelerations is something to think about because it's highly parallelizable. I'm probably running out of time, so I'll just pop over to the code and let's see some code running, right? Don't want death by PowerPoint. So, okay, so think about, say our problem is we want a camera to watch a chess game and figure out what moves are being made. So the input is a video sequence of a chess game. The output is like the, what do you call that, algebraic notation chess moves, just the text. This move was made, this move was made. Let's see, so I'll just go ahead and run this. And this first method was not successful yet, but so this is kind of the initialization phase. What what we want to do, and I kind of wanted to have some interaction here, but I don't want to take too much time. But so you can think about solving it different ways. One, you could say, okay, then I need the algorithm to look at the image and say, the knight is here, and the pawn is here, and the bishop is here, and so then you'd be looking at some machine learning, definitely, probably CNN. But if you look at something like a top view, it's very hard to distinguish, say, the queen from the king, and especially you have different chess sets, and if you're wanting to support different chess sets, they're going to be different shapes, and so. But if you think about it, if you know the initial positions of the pieces, which we do in chess because it's always the same, then all you really need to know is which square is occupied and which is not occupied, because when you move a piece, then that square becomes unoccupied and this one becomes occupied. So then you can figure out, oh, well, that was a pawn. So yeah, so it's still a pawn, didn't change. So this initialization phase here, what we did is, so we want to, this is a segmentation problem, right? We want to, or classification. We want to classify each square as occupied or unoccupied. So basically we ask ourselves, what's the difference between an occupied and an unoccupied square? Like if you had a black and white checkerboard with green and red pieces, it'd be pretty easy to distinguish. You just find the green pixels and the red pixels and threshold. But most chess sets are not as forgiving. So what I've done here real quick is taken a background, no, I didn't take a background snapshot in this case. I wanted to be able to start from the initial positions. What we could have done is taken a snapshot of the board, right, and then just use background subtraction to see the differences. But what if we wanted them to not have to clear off the board and then start the device and then put their pieces back on? So what we've done is there's actually an OpenCV function called find chessboard. Let's go ahead and look at the code so you're not just looking at pictures. And so we have a video. I wrapped it just so I could resize it consistently for the different functions. So there's a NuGet package for this. OpenCV Sharp 3 is OpenCV 3.x. There's also just OpenCV Sharp, which is OpenCV 2.x. But if you just search for OpenCV in the packages, you'll find a NuGet package, and then you can get going. So 2 steps, basically. There's an initialization step where we have this chessboard model initializer, and we give it the video stream. It takes as many frames as it needs to initialize, and then we have a chessboard model as the output, and that'll be used by the next step, which is to watch the whole chess game. And there's a piece segmenter, for lack of a better. So if you look at, let me just, the only thing about OpenCV, it's a little bit archaic, like for example in the user interface, separate windows. So what we've done is we found the chessboard. There's actually a find chessboard, and you give it how many squares you're looking for. In this case, we're looking for a 4x8 chessboard because that's all that's available, that's visible. It won't find an 8x8 because of the pieces in the way. First, we do adaptive threshold. Remember, the adaptive takes care of this lighting problem where it's brighter here and darker here. So we have a nice black and white chessboard here. We use that function then to find the chessboard points. So it gives you an XY image location for each corner point in this open chessboard area. Then from that, since another requirement I kind of gave myself, I guess, was not to require a perfectly top-down view. In that case, you could kind of count on X's and Y's being aligned, right, and not rotated. But with a little bit of 3D perspective like we have here, you take those points, and let me show you that part. It's kind of interesting. Yeah, so let me just walk through. You take your frame, convert it to grayscale, BGR to gray. We do our adaptive threshold, and then find the chessboard corners. So we give it the pattern size, which was 3x7, because you're giving it pattern size in corners. So there's 3x7 inside corners in that empty chessboard area. it gives you a list of points. Those are floating point XYs, where those corners are found in the image. Once we find it, now we create a model of those board points in world coordinates. So we're just going to take and we're going to say that we found skipping rows 0 and 1 where the pieces are. We found row 2. So we're going to set x to 2, column to 1, and then x to 3, column to 1. So we're going to build this model of this is what a chessboard corners look like, and it's just a flat model 1, 2, 3 type of thing. And when you have that, then you give this to this find homography function, which it'll take the points that were found in the image and then take your model and say, this is what's really out there. Now tell me what's the three-dimensional transformation that gets me from my model to what we found. And so that gives you back a 3x3 matrix, which just tells it how to rotate and perspective transform. So then once we have that, then what we can do is this other stuff here. Like create this board model. This was rendered, and so we took those. Now we filled in the whole board. See, we actually only found the middle section, but then we extrapolated those points and then applied our matrix to transform it. So we have a background model that we can subtract theoretically from this to get the differences, even though we had these pieces in the way. This is a mask, and I've left some margin to allow bleeding, because we don't care about those. Okay. Then I tried, next step in the initialization process, I tried to take a histogram of what colors are present in a black square containing a white piece, and how much of each color, or in a white square containing a white piece, and all those 4 combinations plus the 2 empty squares. So here, now we're taking this mask and grabbing all the white pieces on black squares, and we're going to take a histogram of that. This is just a kind of a crude machine learning algorithm. And then we look at the white pieces on white squares and get our histogram, and then we go to the black pieces, black on black, black on white. See that mask changing there? And then we do the same for the empty squares to get what those look like as a histogram. And a histogram is just saying, well, most of you are probably familiar, but it's just saying how much red is there, how much blue is there, and so forth. And then the idea is then to be able to have that model and look at each square and say, oh, that's a black piece on a white square, or that's an empty white square. So the difference is irrelevant here. Here's the sad result, and there may be a bug currently, but the gray squares are supposed to be the empty squares, the white's supposed to be the white pieces, the black pieces, and our little classifier didn't work, sadly. But so just with a few little 3-line changes, we can uncomment the foreground segmenter version. So we're going to do the same 2 steps, but we're going to just take a video where we have the empty board available and get our background model. So we've gotten our background model of the empty board, and now we can diff that with the current frame. So you can see the differences down here. If I can speed this up. Sorry, you're going to have to watch me put pieces on a chessboard. But then over here, what we have is, we're not trying to differentiate black or white pieces, we just have square occupancy. Now, obviously we don't care when someone's making a move, their arm's going to be in the way, they can make all kinds of clutter. So you can just detect when there's large motion over the board and say, okay, we're not going to look right now. And then when the arm's gone, we can go back to, okay, so now here's our model. See, it's a nice representation. that piece just moved up, and then this piece just moved down. And so this is our model of what's happening in the chess game. Now,
Formidable opponents.
what's that?
Formidable opponents.
There you go. Thanks. Yeah. Now here's a problem. Notice these two squares say they're occupied, but oops, only this one is, not this one. Can you tell from the image what happened? Yep, the shadow. The shadow of the knight came over here and made a big difference in this square. So it said, oh, it's occupied. So these are the kinds of challenges you work with in computer vision, and lighting problems is a common one. If you can control the lighting, you could have nice soft lights that would reduce shadows, and maybe this would work really well in that case. Otherwise, you're looking at probably using a CNN, like a convolutional neural network, to try to just to classify if a square is occupied or not. But
Do something along the lines of, we know that there are X number of pieces out there, reduce thresholds until we get that number of pieces.
yes, an optimization to that number of pieces. That's a good idea there. As long as you can count on them not making any illegal moves or
Yeah. Exactly.
yeah.
And you'd have to anticipate for what happens when you remove a piece from the board.
Yeah.
That versus there's really a shadow.
Right. Yeah, and there's all kinds of like non-computer vision algorithms that would have to take place after we get this model.
Yeah.
Right. Yeah. But yeah, that's a good point, and that's a common type of algorithm, optimization. Yeah. Other questions or thoughts?
I guess for something as specialized as this, would it be, I guess, a waste of time or worth it to say, okay, well, you can find your 4x8, can it then, I mean, there's only one way to set up a brand new chessboard, can it just extrapolate from there and know, well, it can tell the white pieces from the black pieces and that's all, but really, you know exactly which piece is where, and then
Mhm.
if you can detect, okay, this piece was here and it was here, and I know this is a pawn.
Yep.
So kind of go from there, and even like if it's unsure, it can check like, oh well, this was a knight, and knights can only move this way. So
Yeah, you could use that information as well. Yeah, that's very true. And in fact, and so all you really need is just that binary representation of is there a piece there or is there not, and then yeah, like you said, from their initial positions, you know that this square was a pawn, so this is a pawn. Yeah.
Isn't there some, I don't know, maybe it's the Jetsons or something, where something like from the 60s or 70s of gaming in the future where you could play chess with someone across the world, or what it was just like a chessboard, I don't know, hooked up to a phone line or something, and when they moved, I don't know if it was weights or it could detect what piece moved where, and it would transmit that to the other
Oh
one.
yeah,
Split
that's
the
cool. I don't remember that, but
thing. I don't know if it actually existed or it was just some
Yeah.
thing.
yeah, I've seen a robot that can play chess. It can pick up pieces and move them and everything. But that, oh, I forgot what I was gonna say.
Well, wasn't that part of, I don't know, 10, 15 years ago, they did that thing with the NHL, tried that thing with highlighting the puck when it would
Oh, yeah.
go behind, so you could tell if it would go behind the plexiglass, or not the plexiglass, the wall, it would still kind of highlight behind it. It was kind of, I guess they stopped doing it for some reason, but
Yeah.
that has to be, something like that was, I guess, what I was talking about with something as specialized. If you know, like, oh, this is only going to be used for hockey, could that be, like, something a lot easier? Or I guess with that,
Yeah.
you kind of even have just a sensor, a motion sensor in the puck. Or
Yeah, they
something.
might have, other than computer vision, they might have RFID or other
So
things.
something as, I'm sure that's how the first down line on a football game works.
Yep, you can definitely computer vision there.
Being able to know that this is what a football field looks like has to be
Right.
a lot easier to process it.
Yeah, and that's a great point. Like when you're looking at computer vision algorithms, you're always looking at your constraints and what you don't have to figure out, and you want to reduce how much you have to solve as much as possible. And so maybe you're balancing hardware costs. But for example, in the chess problem, if you use 2 cameras, then you'd have depth, and then it'd be really easy. You just take slices of the depth above the chessboard and see where there's pieces, right? And so with the right hardware, it can oftentimes make the algorithms a lot easier.
More processing costs than that approach too, it's a bit more challenge, right?
Yeah, that's true. Although it might be less processing because it's easier. And so,
Okay.
yeah, sometimes more sensors will make the processing really simple, but yeah, other times it will multiply it. And so,
Use all the same techniques and functions that they use to do, like the driving cars and
yep, yep,
automatic, like get your brakes if you're not paying attention.
yep,
stuff.
that's all computer vision for sure, and LiDAR and cameras a lot of times. Yeah, so that's a really a fascination for me.
Is that CV used for that kind of stuff, or is that just
Yep.
hobby type?
It's used in a lot of real applications, OpenCV is, and they have builds for mobile. Most of your mobile apps that use computer vision are using OpenCV, but they have builds for desktop, and people are using them on servers and stuff. Yeah, so it's probably the most commonly used. That and MATLAB, but MATLAB is more for the scientists trying to figure out the better algorithms and stuff. Yeah, in fact, there was a really cool video. I thought I had one of some self-driving car stuff. But yeah, you can find a lot of that stuff out there. I mean, that's a tough problem, the self-driving car stuff. But speaking of CNNs, they're using those to segment roads really well. Well, anyway, but there's a video of what's it called? It's called segmentation road. Let's go. Yeah, they're using something like a convolutional neural net, and the different colors represent the different parts of the scene. The road is a color, and the lanes and the cars is a color, and the trees. And so there's some really cool stuff going on there. And then, of course, you need lane detection to figure out how to stay in your lane and all that. Yeah. Yeah. Any other? Oh yeah, did I run that? Oh yeah, I did. So any other questions?
Like an MP4 file or something that you video? I mean, how does that
Yeah.
into your program?
Yep. So OpenCV has the capability of loading images and videos. So this video source, I wrapped this in here, but this is from OpenCV right here. This video capture. So you just give it a file path, or you can give it other things, and then you just grab your next frame. Oh, that's initialization. Yeah, video capture, read, frame. The API is a little bit archaic. It's a little bit C++-ish. This has been around since 2000 or so, and so it's not. It doesn't feel really great. It's definitely not functional, but it does a great job, of course. But yeah, so right here, you're reading the frame every iteration. If it returns true, then it still has more frames. So it's really easy to use. But yeah, it's a little weird. It takes some reading the documentation. Fortunately, they have really good documentation on all their functions. So, yeah. Any other questions or?
Anything else other than your chessboard interpreter?
Chessboard. I've done the motion tracking. I've started on a number of things. Let's see. Well, I was at a job where I translated MATLAB algorithms into C++, OpenCV. It was for video stabilization and denoising. And then I played around with visual odometry. I was trying to build, back in 2012, 2013, build like an AR, outdoor AR large scale, where you walk around, kind of like HoloLens basically, but for outdoor wireless. And so I was using visual odometry with an IMU sensor. So when you're solving a problem, you always got to think outside the box of computer vision and see what other sensors you could use. But a 9-degree of freedom IMU had accelerometer, gyros, and all that. It would combine that with the visual odometry to try to figure out where you're going. I ended up ditching that project for another one, but yeah. And then I played around with a number of things, but yeah. I guess about all I got, I guess. So, yeah, thanks for your time. It was useful. Thank you.
Actually, do have one